Welcome to the second week of this course. So, in this week we will discuss micromechanics of composite plies. So far we have seen that when we try to analyze composite, there are several challenges. The first challenge comes because these materials are non-homogeneous, because it is made of two or more materials and their properties are different. The second set of challenge comes because these materials are anisotropic, their properties are different in different directions. And then we have seen that a composite laminate is made of various plies or lamina, and each lamina has different fiber orientation. So, that is another set of challenge. Now, in this week we will discuss about micromechanics, which aims to address the first challenge due to non-homogeneity. So, this is how the analysis of composite goes. At first we try to find out the homogenized properties. That means, we have composite made of different materials with different properties. So, that is hard to deal with. So, what we do is we try to figure out one property which applies to the composite as a whole. So, for example, we will find out one density instead of densities of fiber and matrix, similarly for elastic modulus, Poisson's ratio and so on, and that process is called homogenization, and that is something we do by micromechanics. So, that study is called micromechanical study. Now, we can get the homogenized properties by homogenization through micromechanics, or we can directly get the homogenized properties by experiments also. So, experimental determination of homogenized properties. So, using one of these two approaches, we can get the homogenized properties of composite ply. Once we have that, then the next step is to do a macromechanical study of ply. So, macromechanics of or macromechanical analysis of ply. In this step, we look into the challenge due to the anisotropy. So, after we get the homogenized properties, we will see that these properties are different in different directions. So, how to deal with that? That is what we do here by macromechanics of ply. Once we do that, then we go for analysis of laminate. So, we have found out the homogenized properties of ply, then we have seen how we can analyze the anisotropic behavior, and after we get the individual anisotropic ply properties, then we can see that how we can analyze a laminate which is made of various plies, and with the possibility that each ply can have different fiber orientation. After that, finally, we can analyze a composite structure. That means, a structure made of these laminates. So, we have a bottom to top approach. So, we will start from the very bottom, where we see the plies as something made up of two or more materials, and then we will see how we can find out the equivalent composite property. Now, the question is, what are the properties that we homogenize? So, if we list down the properties which we homogenize, so these various properties include density. Now, density is something which we will need when we do dynamic analysis of composite. Then comes our elastic constant. So, whether we do a static analysis, dynamic analysis or stability analysis, we always need the elastic constants. So, these can be elastic moduli Poisson's ratios. Again, as we know that these plies are anisotropic, so they have different elastic modulus in different directions. Similarly, different Poisson's ratio in different directions. So, that is why these are in plural. Then there can be strength parameters. For example, this can be tensile strength, compressive strength, and so on. Etc. Now, again these materials are anisotropic. So, the tensile strength in a certain direction can be different from the tensile strength as compared to other direction, and same thing goes for compressive and other strengths. Then thermal expansion coefficients, similarly moisture coefficients, moisture expansion coefficients, all these properties we need. Now, in this week we will focus mainly on these two parameters. Later on, further when we discuss about the failure of composites, then we separately discuss the micromechanics related to the various strength. Similarly, when we separately discuss thermal and moisture effects, at that time we will discuss the micromechanics which is relevant to this thermal and moisture expansion coefficient. So, this week focus mainly on density and the elastic constants. Now, there are various approaches that we generally use to derive these homogenized properties. So, for example, there are strength of material based approach, exact solution using theory of elasticity, numerical techniques, and so on. But this course mainly focus on the strength of material based approach and rule of mixture. We will have a brief overview of rest of the approaches later on, but most of the derivations that we will do will be based on the rule of mixture or strength of material based approach. Now, before we go there, we need to understand some definitions, and which we will come across repeatedly in micromechanics. The first one is volume fraction. As the name suggests, it is a fraction and it is related to volume. So, we have separate volume fractions for fiber and matrix. Say our composite is made of a certain fiber and certain matrix. So, the fiber volume fraction Vf, we call it fiber volume fraction, and that is defined as the volume of fiber divided by the volume of composite. So, here capital V denotes the volume fraction and small v denotes the volume itself. So, say we have a composite, its size is 2 centimeter cube, and within that 2 centimeter cube, say our fiber occupies 0.5 centimeter cube, then the fiber volume fraction will be 0.5 divided by 2. So, that means 1 by 4. So, fiber volume divided by the composite volume, and our composite is made of matrix and fiber. So, the total volume is again matrix volume plus fiber volume, and that is what we called fiber volume fraction. Similarly, there is something called matrix volume fraction, that is matrix volume by composite volume or the total volume, and that is equal to the matrix volume divided by the matrix volume plus the fiber volume. So, Vm denotes matrix volume, the volume itself, not any ratio. Similarly, Vf is fiber volume and Vc is equal to Vm plus Vf is equal to total volume of the composite. Now, one straightforward conclusion of this result is, if we just add Vm and Vf, so Vf plus Vm becomes Vf by Vc plus Vm by Vc, and that is equal to, in the numerator and denominator we have both Vc. So, the total is 1. So, these two fractions on being added gives us 1. Now, similarly, like we have defined the fiber volume fractions, similarly there can be weight fractions also. So, weight or mass fractions. Although we use the word weight here, but that is essentially mass. So, in some book we will see it is called weight fraction, in some book we can see it is called mass fraction. The definition is very similar. So, weight fraction of fiber is equal to the weight of the fiber or the mass of the fiber divided by weight of the composite. So, Wf divided by Wm plus Wf. So, this is fiber weight fraction, and again the capital W means the fraction, small w means the weight itself. Similarly, we have matrix weight fraction, and that is weight of the matrix divided by weight of the composite, and again that is essentially Wm divided by Wm plus Wf, and this is matrix weight fraction. Now, we can write Wm, that is equal to matrix weight or matrix mass, small Wm is equal to fiber mass, and Wc is equal to the total mass or total composite mass. Again, needless to say, if we just add these two fractions, they have to be 1. Now, we will see, if we have the fiber arrangement known in the composite, can we get the volume fractions. So, we can say that we are going to derive the volume fractions from fiber arrangement. So, using simple geometrical observations we can do that. Let us say this is our composite, and it has fibers laid up, and they just are they just aligned in this direction, in the lengthwise direction. Now, if I take a cross section at a certain plane, And if you look at the cross sectional view, that means if we view it along this direction, what we would see is something like this. And let us assume that the fibers that we have are cylindrical. So, there are cylindrical fibers with equal spacing and they are put in a square form. That means, the spacing between them, if it is S is the center to center spacing between two cylinders, and similarly the vertical spacing is also S. And let us say that each fiber has a diameter d. So, we are separately showing it for clarity. Now, if I connect the centers of these closely located fibers, and then you can create one unit. And if we separately study one unit, what we see is something like this. So, each unit gets one quarter circle like this, and this dimension is S, this dimension is S, and this is nothing but d by 2, half of the diameter. Now, these are the area occupied by the fiber, and whatever is left is our matrix. Now, area occupied by fiber, we can call it small a suffix f. So, area occupied by fiber is, each of them is a quarter circle. So, their area is pi by 16 d square, and there are 4 of those. So, area occupied by the fibers is pi d square by 4, and total area of the composite is this entire area, that is a square. So, we can say that there is, we can define something called area fraction, area occupied by fiber divided by area of the composite, and that we call it pi d square by 4 a square. And now, if I find out the fiber volume is just this quantity multiplied by the entire length. Similarly, the composite volume is this quantity multiplied by the entire length. So, we can definitely say that the area fraction is equal to the volume fraction also, and that is pi d square by 4 s square. Now, let us say that we want to make this composite fiber dense, that means we want to keep as much fiber as possible. In that case, the cylinders has to touch each other, very densely packed fiber arrangement, but no matter what we do, there is bound to some space being left, some space would be bound to be left. Now, we can say that S is equal to D, because this intermediate length is just gone. So, in the maximum case, V f max is going to be A f max, which is equal to pi by 4, because D is equal to x. That is for cylindrical fibers arranged in a square fashion. Now, we will study if the same cylindrical fibers are arranged in the form of triangles. Say we have fibers here and fibers like this. So, we can connect the centers and make a triangle and the spacing is S. So, this is a triangle which has all the sides of same length. Now, again if we study that triangle, this is a magnified view and we can see that each corner has a piece of circle. Now, this is 1/6 of a circle because this angle is 60 degree. So, 360 by 66. So, this is 1/6 of a circle. Now, we can say that the fiber area is pi by 24 d square, that is area of each circle, and there are 3 of those. So, that gives us pi d square by 8, that is area of the fiber, and area of this composite is area of that triangle is root 3 by 4 s square. So, that gives us that the fiber volume fraction is equal to the fiber area fraction, and that is equal to pi d square divided by 8 divided by root 3 by 4 s square, and that gives us this expression pi d square 2 root 3 s square. Now, again we can do the same thing. If we want to find out the maximum fiber volume fraction that is possible with this kind of arrangement, then we have to arrange it in this fashion, and again in that case our D and S are going to be same. So, Vf max for cylindrical fibers arranged in triangle formation is pi by 2 root 3. Now, one thing to understand is we said that this Vf is equal to Af because in the perpendicular direction the dimension is same. So, this is possible because these fibers are, I mean the fiber arrangement does not change if we go through the perpendicular direction. But if the fiber arrangement varies along the length, that means if the fiber arrangement varies along this dimension, then we cannot say it like this. So, nowadays we are talking about these variable spacing fibers or curvilinear fibers. In that case, these observations need some modification or extension. Now, we will talk about density, that means how can we homogenize density of composite. So, we will homogenize density with the help of something called rule of mixture. So, we know that weight of composite is equal to weight of fiber plus weight of matrix, and let us say that the composite is made of fiber and matrix with fiber density being rho f. So, density of fiber and density of matrix is rho m. And then we can say rho c as density of composite. Now, here the goal is that we will find out one quantity rho c which can be treated as the equivalent density of the composite. So, the weight of the fiber is or mass of the fiber is density multiplied by the volume of fiber. Similarly, the mass of the matrix is density of the matrix multiplied by volume of the matrix, and on being added that gives me the total mass of the composite. So, if we think of a quantity rho c which is the equivalent density of the composite, and if I multiply that rho c by V c which is the total volume of the composite, that should give me the total mass. Now, we can just take this V c here. So, that becomes rho f, and we have V f by V c, and that quantity is nothing but fiber volume fraction, and then plus rho m, then V m by V c, and that is nothing but matrix volume fraction. So, this is the homogenized composite density in terms of the volume fractions. Yes. Now, we can derive the same quantity in terms of the matrix volume fractions, the weight fractions. So, for that what we can do is we can define the composite volume as V m plus V f, and then the volume of the matrix is mass of matrix divided by density of matrix, and we have volume of fiber as mass of fiber divided by density of fiber. In the left hand side V c also we can write weight of the composite divided by the density of the composite. Then we can take this W c here in the denominator, and that gives us weight fraction of matrix divided by density of matrix plus volume fraction of matrix divided by volume fraction of fiber divided by density of fiber. Now, we will find out some relations between the weight fractions and volume fractions. Since fibers and matrix have different densities, so the weight fractions and volume fractions are going to be different. So, weight fraction, so relations between weight and volume fractions. So, to derive that relation, let us go back to the definition of weight fraction. So, weight fraction of fiber is equal to weight of the fiber divided by weight of the fiber plus weight of the matrix, and that we can write as weight of the fiber can be written as volume of the fiber multiplied by density of the fiber. Similarly, weight or mass of the fiber is again this, and likewise we can write for matrix. Now, if we divide the numerator by volume of composite and divide the denominator by volume of composite, that gives us V a by V c in the numerator, and that is nothing but fiber volume fraction. So, we can write this as density of fiber multiplied by fiber volume fraction. Similarly, in the denominator we have density of fiber multiplied by fiber volume fraction plus density of matrix multiplied by matrix volume fraction. In the same way, we can define relate the weight fraction of matrix as this. Just in the numerator we have to change rho f V f to rho m V m. Now, we will do the inverse relation. So, we have fiber volume fraction, which we can write as volume of fiber divided by the volume of fiber plus volume of matrix, and volume of fiber is nothing but weight of fiber divided by the density of fiber. Similarly, here also we have weight of the fiber divided by the density of fiber, and then we have weight of the matrix divided by the density of matrix. Now, again the numerator can be divided by weight of the composite and the denominator can be divided by weight of the composite, and that would give us capital Wf, that means weight fraction of fiber in the numerator. So, capital Wf by rho f in the numerator, in the denominator we have rho f by rho f, Wf by rho f plus capital Wm by rho m. In the similar fashion, we can find out the matrix volume fraction in terms of the weight fractions as this. Yes. So far we have looked into the definition of weight fractions, volume fractions, their interrelation. We have seen if we are given the fiber arrangement, how we can find the volume fractions, and also we have found out the equivalent or homogenized density of composite. So, with that I would like to finish this lecture here. Thank you.